Hey there, Mr. Sutton here with the AB Calculus 3-3 Extra Practice Number 3 solutions on differentiability, Part 2. On this one, we want to know if this function is differentiable at the border value 1. So let's first figure out if it's continuous at that point, because that's a prerequisite to being differentiable. So we'll check the left and right limits and the function value to see if those match up. Left side limit at 1 is just going to be this less than 1 function, so 2. And then the right side limit at 1, well, now we're using the greater than 1 rule, so that's going to be 2 times 1, which also happens to be 2. Function value, which we have to include for continuity, that's going to be the same as the left side rule, so 2 again. So we see here that the limit as x approaches 1 and the function value, they both exist and they equal each other. Therefore, our function is continuous at x equals 1. Next, let's see if the slopes of these rules are going to match up. So now I need the left side limit as x approaches 1 of f prime of x. So that's going to be taking the derivative of this less than 1 rule. Derivative of 2, since 2 is a constant, that's just going to be 0. And then for the right side limit as x approaches 1 for f prime, now we're taking the derivative of this after 1 rule. Derivative of 2x is 2, constant value of 2. We see here that the limits do not match up for f prime, so therefore this function is not differentiable at x equals 1. On this problem, we want to know if this piecewise function is differentiable at the border value -2. Let's start by seeing if it's continuous. So the left side limit as x approaches -2, that's using the less than -2 rule. So this is going to be -1.5 times 2 squared, or 4. So -1.5 times 4, that's going to give us -6. Next, we need the right side limit at -2. That's using the greater than -2 rule here. So that's going to be 6 times -2, which is -12, minus 5, so -17 overall. And that's not even close to our left side limit. Since the limits don't match, the overall limit as x approaches -2 does not exist, which means that our function is not continuous at x equals -2. Well, since continuity is a prerequisite to differentiability, if we're not continuous at -2, we are not differentiable at x equals -2. On this problem, we're trying to figure out if the function's differentiable at the border value 0. So to do that, let's first figure out if it's continuous there. Let me get the left side limit at 0. So that's going to be plugging 0 into this first function, the less than 0 function. 0 squared is going to give us just 0. Next, let me check the left side, or the right side limit at 0 rather. That uses the second rule. Plugging 0 into x just gives us 0 back. And then finally the function value at 0, f of 0, that just uses the first rule again, giving us the left side limit again of 0. Okay, let's also check out the, well, first off, let's state that this is continuous. So my limit matches up, so that means it exists, and it matches the function value 0. So that means I can conclude that we're continuous at 0, but I still haven't shown we're differentiable. For that, I need to check out the limits of the slope at 0. So left side limit of f prime as x approaches 0, that'll use the derivative of x squared, so that'll be 2x. And then plugging 0 into that, 2 times 0 comes out to 0. We also need to figure out the right side limit of f prime. So that'll take the derivative of this x rule, which is always 1. Since the right and the left side limits do not match up, that means our function is actually not differentiable at x equals 0. For this problem, we have this piecewise function here with some k's and some b's kicking around in there. We want to figure out values of k and b that make the function both continuous and differentiable across the whole domain. Okay, well, this whole domain should make us a little bit suspicious. Let's just make sure there's nothing else going on other than possible discontinuities at the border value. So the first rule is a polynomial, so it's continuous everywhere and differentiable everywhere. Same thing with the second rule, so we actually don't have to worry about anything other than the border value. All right, well, let's basically pretend we're testing for continuity. We're going to end up with some equations that may have k's and b's in them, and we'll use those equations to solve for k and b. Let me consider the left side limit as x approaches 1 of f of x. So that's going to be plugging 1 into this first rule here. So that'll be 1 squared plus k minus 3. That'll be k minus 2 if we simplify. Now the right side limit at x equals 1, that's going to use this second rule. So we have 3 times 1 plus b, which is just 3 plus b. And I also have to show the border value. I mean, it's multiple choice, so I guess I don't have to show the function value. But let me show it anyway to prove that this is really going to be continuous. So that's going to use the first rule again. So we're doing f of 1 now. Using that first rule, we again get k minus 2. So I know that if this is continuous, that means the limit and the function value have to match up. So that means for the limit to match up, that means that k minus 2 has to equal 3 plus b. And if that matches up, then it's going to match the k minus 2 over here. So this is the first equation that we can write. Now we can't really solve this because it has k's and b's in it. So we actually move on to figure out the slope limits at this point and match those up. So my left side limit of f prime, that's going to be using this first function and taking its derivative before we plug in 1. So that's going to be 2x plus k. And if we plug 1 into that, coming from the left, that's going to be just 2 plus k. Now I also need the right side limit as x approaches 1. That's going to use this second rule. And if I take the derivative of this thing, b is a constant, so it gets differentiated away. 3x just turns into 3, so that is going to be my right side limit no matter what I want to plug in there. Since these limits have to match up, 2 plus k and 3 must equal each other. So that means that k has to be positive 1. Well, now that I know the value of k, I can plug it in back to this first equation and solve for b. So plugging it in here, I've got 1 minus 2 equals 3 plus b. 1 minus 2 is negative 1. Subtract 3 from that, b equals negative 4. So we have a k value of 1, a b value of negative 4. That gives us answer choice D. For this problem, we're given this piecewise function, and we're asked which of these statements about it is true. Now, if you look at these statements, we're talking about continuity and differentiability. So basically, we're going to have to run some continuity and differentiability tests on this thing at x equals 5. But just doing a quick scan of the answer choices. Continuous and differentiable, okay, it's possible. Continuous, not differentiable, also possible. Differentiable, but not continuous. Well, that's just baloney. Something that's differentiable is automatically continuous. So you can eliminate choice C right off the bat without doing any work on this one. And then choice D, defined but neither continuous nor differentiable, certainly possible. So let's see what kind of issues we're dealing with at x equals 5. We'll start by checking for continuity, which means we have to see if the limit exists at x equals 5, which means we have to check the left versus the right side limits. So limit as x approaches 5 from the left, that's the first thing we'll check. That's using this less than 5 rule. So we're plugging 5 into this first rule here. That's negative 5 squared plus 3. So negative 25 plus 3 is negative 22. And then we have to check the right side limit at 5. So that's using the after 5 rule, the second rule. That's going to be negative 10 times 5, which is negative 50. Plus 28 also gives us negative 22. And let's just throw it in there. The function value, f of 5, that's going to just use the same rule as the left side limit used, so this first rule. So again, we get negative 22. Well, we see here that since the limit exists and the function value, and they all equal each other, therefore, our function is continuous at x equals 5. So we can eliminate choice D, which said that it wasn't continuous. And that means we're down to choices A and B. Are we differentiable or not? So to check the rest of the differentiability here, we need to take a look at f prime and see what the limit of f prime is doing as we approach this border value from the left and the right. So let's take a look at the left side limit at 5 of f prime. That's going to be taking the derivative of this less than 5 rule and plugging in 5. So this will be negative 2x that we're figuring out as x approaches 5. That's negative 2 times 5, which is negative 10. And now we have to check the limit as x approaches 5 from the right of f prime. So now we're taking the derivative of this second rule, and that's just going to be a constant value of negative 10 using the line rule here. Well, those limits match up. Therefore, our function is in fact differentiable at x equals 5. So that's going to be choice A, continuous and differentiable. There we are. For this problem, we're given this piecewise function, and we want to know which of these statements about it is true. And these are all asking about continuity versus differentiability. So let's just read these answer choices real quick and see if we can eliminate any right off the bat. So continuous, neither continuous nor differentiable, that's possible. Continuous but not differentiable, also possible. Differentiable but not continuous, that is not possible. If something's differentiable, it automatically is continuous. So we can eliminate choice C right off the bat. And then D, both continuous and differentiable, also possible. Okay, so let's check continuity first, because if it's not continuous, it's not differentiable. So for that one, we're going to check the limit and the function value at x equals 2, the border value. Left side limit as x approaches 2. That's using the less than 2 rule here and plugging 2 into it. 3 times 2 plus 1, that's going to be 6 plus 1, or 7. Now to check as limit as x approaches 2 from the right side, now we're using the after 2 rule right here. So that's 5 times 2, which is 10, minus 3 is also 7. And let's throw in the function value, f of 2. That just happens to be the same as the left side limit. It shares the same rule as that one, so it again comes out to 7. So we see here that the limit exists, the function value exists, and the limit and the function value are equal to each other, meaning that our function is indeed continuous at x equals 2. So that means we are down to choices B and D. We have continuity. We just want to know about the full differentiability. So for the other piece of it, we need to look at the limit of f prime as x approaches 2 from the left and the right. So left side limit of f prime now, the slope of this first rule, this before 2 rule, we're just taking the derivative of 3x plus 1 and plugging 2 into it. Well, the derivative of this is just the constant value 3. Can't really plug anything into it. So that is our first derivative here. Now the limit of f prime as x approaches 2 from the right side, now we have to use this after 2 rule and take the derivative of 5x minus 3. That's going to be 5, constant value. And we see we've got a problem here. The left side limit of f prime and the right side limit don't match, which means that our function is not differentiable after all at x equals 2. So we do have continuity, we do not have differentiability. That means we are choosing answer choice B.